We're back in part B of my final project, Maze Solver. If you haven't seen part A, then refer to part A. It should be under my videos. So at the end of part A, we were talking about the user inputs of the start point and the end point. So I will be posting this code as well to GitHub. There's a lot of comments within the code, so if you're interested, you can look at that. But I'm going to be brushing over some of these more redundant loops that are not very important to the project. But if you're interested, you can always check them out. So now that we've gotten the start point checked that it's valid and everything within the maze and not a wall, and similarly for the endpoint, not a wall inside the maze, etc. We are going to start solving the maze. So now that we will also mark the endpoint as an @ symbol, and if they don't pick the specified exit, for all of my mazes have a specified exit. I'll demonstrate what that is very quickly. They all have a specified exit here, but if they want to use another exit, say for instance here, or have their treasure be there, we're going to block off the old exit so the cursor can't escape and cause us problems. Okay, so now we've got that, then we're going to call our solve method. So our solve method obviously is going to call our take in maze, our start row and our start column from our user, and then it's going to display our maze. And well, no, not yet. If our explorer gets a true, then we're going to display the maze and the path that has been found. And if we don't find an exit, which isn't possible for my mazes, but if it was, we would print no solution. So this is a meat of the project, as it were. This is the explore method. This is the method that is using recursive backtracking. This is the method that is going to be solving the maze. So like the solve method, explore takes in a maze, a row, and a column. So this is a sort of our pseudo base case if we find a wall, or if the point has been already met, or have already been explored, excuse me. I wouldn't say base case, but this is what allows us to know what is a true path and what is not. And then we have, using our isExit method in the maze class, use the isExit method, and that lets us know that we have reached our base case. And then once we know we've reached the exit, we will print out our path to reach that point. Okay, so but if none of these are met, we're going to set the row column, so the square that we're at, as true. So we know that it's been visited, and then now we're getting into the recursion part of this method. We search until we get a failed case, which is either a wall, but more specifically a dead end. So like in that example I showed you previously, let's pull that up. If we get here and we have nowhere to go because these have been searched, and this is a wall, this is a wall, this is a wall, then that gives us all these are false, and then we start searching this way. So there's that. We will keep going until we get stuck or we find the exit, essentially. A southwest northeast approach where I'm going to search in that order. Um, I found that using some sort of box type structure where you kind of go around the compass, as it were, in a box, you get better results. Um, I'm sure if you mix that around and formed a box, but in a different way, I figured out there's 24 different box configurations. All of the run times are going to be about the same, averaged out if you used multiple different maze setups. So as long as you're doing a box type of solving, I think you should be fine. Here we go. So this is our recursion here. So we're going to call our explore again, but we're going to do it in the south direction, which is a row down. Obviously, we're going to make sure that new square, excuse me, isn't a wall or hasn't been previously explored. We're going to check if it's the exit, and if that's not true, we're going to set the current row, this row, to explored. So then we're going to call south again, and we're going to keep calling south until we cannot call south. Which case, that means either the maze is a wall, we've hit a wall, or explored. But if we're going south, we're not going to get an explored. We're going to hit a wall eventually. So when we hit a wall, we're going to start going west. We're going to go west one. And then if we go west one, we come back, check if it's a wall or if it's been explored previously, etc., etc. But instead of calling west again, we call south again. So that's the beauty of recursion, that once you reach a dead end, say in our south case where we go all the way south and we have nowhere else to go, we go west one, but then we start going south again. But that is how that works, and then the same thing would happen if south doesn't work, west doesn't work. Try north. If north doesn't work, we're going to go east. So eventually we are going to find the exit. So we are going to get a true here when we find the exit. And this if block, it's kind of confusing, but this is saying if one of these is true. So if one of these finds the exit, we're going to mark that with an X, so marking our path out. We're going to print the maze. And then we're going to pull a true again. So then all the other recursive calls that have led us to finding the exit are going to start popping off the stack, giving us trues, and then recursively backtracking our way out of the maze. Yeah, and then this is a false case, or if we reach a dead end. But I'm going to show you an example now. It's kind of hard to visualize it in our mind. So we are going to be using, I'm going to try to make this full screen for everybody. We're going to be using the maze 1. It's a little bit simpler of a maze. So that's our maze. And then I kind of designated a starting point for the users so they don't have to guess and try to get inside the maze and not a wall. So we're just going to start there. And then this is our endpoint here. We could obviously pick a treasure point anywhere along the path, but we are going to use the designated exit. So it kind of moves along pretty quickly, but once it finishes solving it, I will go through a couple iterations. So now you see that it's found its path, or found the exit, and then it's tracing its path back towards the exit. So we found our exit, but let's go back to the top. So here's where we start. Here's the exit. So we are using a southwest, excuse me, with all these windows, we're using a southwest northeast approach to solving our maze. So we are here. Excuse me. We are here. We search south, but that's a wall. So we get a false. We search west, which is good. So we move to that point. We search south again, we get a wall. So that's false. Then we search west, which is going to be an open space, so we move there. And we're going to keep getting south is a wall until we reach this point. So we're going to move west because that's our second choice. So we keep moving west until we finally get down this long corridor. Keep checking south, that's a wall. And then finally, once we move west one more, we can move south. So now that we're able to move south, our further calls are just going to be hitting this first if. So we're going to move south rather quickly, down, 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 until we hit this bottom wall, which we will. And then we're going to check west, which is also a wall. Then we're going to check north, which has visited already. So that's going to be false. So that's the north check. And then we're going to check east finally. So then we're going to do the same thing where we check southwest, northeast again. We're going to go south wall, west has already been explored, north is a wall, so go east. So that is what we're going to do, and I think you guys get the general idea. And then, just because the way my algorithm worked, we didn't go. Actually, yes, because north is before east, we actually go up this this dead end. So now that we're working our way up this dead end, when we finally, sorry for the fast scrolling, I'm just trying to find where we finally get to the end of the wall. See, that's the thing about it, is when it's trying to work its way east, and you as a user can see that east is the way to go, but the computer has no way of knowing that without checking these. So it has to go through 3 separate checks before it can go through east. So that's why it seems like it's moving rather slowly. Okay, so we are finally at the dead end, so to speak. So we're going to check south, which is a wall. We're going to check west, which has been explored. We're going to check north, which has been explored. And we're going to check east, which has been explored. So, man, now what are we going to do? So we've gotten all falses for these searches. So then we're going to go to the last time we haven't gotten a false, which is here. So we're going to transport ourselves, as it were, not totally block off, but for the computer's sake, we are not going to say this is a good route to go. So we're going to move ourselves here. So now that we're here, okay, also, now that we are back on track, we are here, and then we're going to do the similar explores that we have been doing until we find our exit. And then once we find our exit, we finally get a true, because during all of this, we're not getting trues, we're getting yeses almost, where it's yes, there's an open space. When we get a true, that means is when we reach our base case. So then all of the paths that we have taken, except for this one, which is our dead end, will be marked as the path out. So now we've found our exit. So now we're going to mark recursively backtrack, to use the jargon correctly. We're going to recursively backtrack our path back to our starting point. So that goes through all of that, and then we finally get to our starting point, and we get an exit found. So that's how the maze solver works. We are going to run it one more time with, we're going to run it one more time with the larger maze to give you a bigger idea of how this is all going to work with a bigger maze. And if I took the sleeps out of the animation, it would show you how fast a computer can solve a problem like this. But it's kind of fun watching it solve it. So we're going to just use the given points to move this along. But you can see, even with the sleeps, it moves pretty quickly. But because this maze is so large and has a lot of dead ends, as you can see, it takes a little bit for it to solve. So I'll speed this part of the video up, so you can kind of just get a time lapse view of the solving of this maze, and then I will come back to you once the maze is solved. Okay, so the maze has been solved. Um, so now we are backtracking our way out, which you can see is quite a long distance. I could have, I mean, this isn't going to be the most efficient route. You could have implemented something along the lines of making each one of these squares a pointer and then using some sort of distance formula to calculate the shortest distance. Obviously, there's multiple ways of solving. Well, it depends on the maze, but some mazes have multiple ways of solving it. And if that is the case, you would probably want to figure out the shortest distance, obviously, because it would be the quicker route out of the maze. But I didn't implement anything like that. So, yeah, if you have any questions, just leave them down in the comments, and then I'll be posting the code to GitHub, and I'll put the link in the description for both Part A and Part B. So thank you. Yeah, please let me know if you liked the video and everything. If I need to explain something to you or anything I could have done better. But yeah, thanks for watching and have a nice day.